to make sure I'm recording this part of the lecture. I think we're live there. All right, and I'm going to screen share. All right, can everybody see the whiteboard? All right, I'm seeing nods, yes, perfect. So let's go ahead and get started on this then. All right, so the first thing that I want to do, this is something that is fair for the test tomorrow, okay? But again, it will not be present on the quiz today, and that is known as the common ion effect. So let's go back. If you look at the initial example, when I was teaching this, I used silver chloride, okay? So silver chloride is a solid, can be in equilibrium with the silver ions and the chloride ions, right? So what common ion effect says is what happens if the silver chloride is present in a solution where one of these two ions is going to be sort of artificially inflated because they're also present in the solution, all right? So what we're going to do in this example is say we're going to have silver chloride and we're going to add it to a solution of silver nitrate. So silver being the common theme here, right? We have an aqueous solution of silver nitrate, and then I'm going to add the silver chloride to the silver nitrate, and I'm going to take a look at its solubility. So what I want to do is see how is the presence of silver already in a solution going to affect the solubility of more silver coming into solution. And general logic would dictate that I should see a decrease in the solubility of the silver chloride, right? Because if I've already got silver being liberated from silver nitrate, and then I'm trying to add additional silver and liberate that from the silver chloride, I'm going to have a bit of difficulty doing that. So another way that we can view this is Le Chatelier's principle, going back to our general equilibrium principles. So what I'm saying is, if I take this in isolation, here's the equilibrium reaction. But what I'm doing is by introducing silver nitrate, I'm pumping this value up. I'm increasing the amount of product that's there. So what is that going to do? It's going to drive the precipitation of solid silver chloride, or in other words, it's going to lower the solubility, right, the dispersal of the silver and the chlorine ions. Does this, before we get into the math, does this make logical sense in regards to what we're talking about? Just shake your head, yes or no. Okay, most people, it looks like they're okay with this. All right, again, if there's questions about this, you are welcome to stay behind for office hours, okay? So here's what we're gonna do. We are going to take a silver nitrate solution, okay? And the silver nitrate solution is going to be given a concentration. The concentration we're going to give this is 8.3 times 10 to the -3rd molarity, right? And now what we're going to do is we're going to calculate the solubility. And when we say solubility here, we're talking about in grams per liter. We're going to calculate the solubility of silver chloride in the silver nitrate solution. All right, so I've got a solution of silver nitrate at 8.3 times 10 to the -3rd molarity. And then I want to calculate what would be the solubility of the silver chloride in that silver nitrate solution. That's what I just theoretically walked through in the image above with the equation, okay? So the main focus here, what I'm gonna be focused on at first is the Ag+, because that is the common ion in effect here. I've got silver coming from both the nitrate as well as silver coming from the chloride. So if the goal is to calculate the solubility of the silver chloride, that's what I want to set the ice chart up for. So I'll say, let's rewrite the equation down here so it's nice and clean. Silver chloride solid is going to be in equilibrium with silver ions that are aqueous plus chloride ions that are aqueous. All right, now Here's where this is going to deviate from what we were initially practicing last Thursday and the first YouTube video that I posted on this. Okay, solids still drop out. There's nothing that's changed on that front. However, normally I would say my solid dissociates, and at time initial, these are both 0. This is where that changes. At time initial, silver is not 0. Silver is now present before I ever add the silver chloride. I have some amount of silver present in the solution, right? Now, the amount of silver that's present depends on how the AgNO3 breaks down. So we're going to pop back up here and say AgNO3 is a solid. Now, in this case, this is not in equilibrium because NO3 is a strong electrolyte. That means it dissociates 100%, similar to something along the lines of HCl. So if you're confused where I'm getting that from, back in General Chemistry 1, there was a general chart that said all nitrates are soluble, most sulfites are insoluble, and then you'd have the exceptions that are listed there, okay? So one of those rules, the top rule on the chart usually, is that nitrates are 100% soluble. So there is no equilibrium or pushback. All of it goes to silver ions, right, plus nitrate ions. Now, this is a 1-to-1 ratio here. So because of that, the concentration of the AgNO3 is also the concentration of the silver. Now you have to be careful, because if there was an example where this had a 2 or a 3 in front of it for the silver as far as the stoichiometric number, you would have to multiply the molarity accordingly, because it's releasing more moles as it dissociates of a given material. All right, but because this is 1-to-1, then we can assume that if it goes to 100% dissociation, all of the concentration for AgNO3 gets converted into concentration for silver as well as concentration for nitrate. So the value in this chart is going to be 8.3 times 10 to the -3rd. Chlorine is 0. Now chlorine is 0, the chloride ion is 0, because the nitrate solution does not have any of that. So I still assume that there's no chloride at the beginning. Now for the change. This is as usual. It's going to be plus x plus x. Okay, and so this is now at the equilibrium. We have 8.3 times 10 to the -3rd plus x, and then just x over here. Okay. Everything should be on track so far as people understanding where this is coming from. We've done this similar to some acids and bases, right? Specifically, when we've done the example with the diprotic acid, there was some initial concentration of H3O plus left over from the first dissociation that we had to bring into the ice chart for the second acidic dissociation. All right. Now, what I would need, you'd have to go get this from the chart, but for the sake of time, I'm going to give this to you. You need to know what the KSP is, because we're going to set the KSP equal to the equilibrium concentration. So the KSP for the silver chloride is 1.6 times 10 to the -10th. Again, you could get that value by going into your charts in the back of the OpenStax book and finding that. All right, now I have to set this equal to, all right, these all have a 1, so none of these values are going to be squared or cubed or anything of that nature. So it'll be the silver concentration, which is going to be 8.3 times 10 to the -3rd plus x times x, all right? Now, you can factor, you're going to get an x squared and an x, and then you could set all this equal to quadratic, but it's easier to use the 5% rule, so let's just take a look at that and see if we make a pass, and if we do, then we'll continue forward with that. So 5% rule says anything that is plus or minus x I can get rid of, okay? So I'm going to get rid of that plus x, but I have to keep this times x here. So that simplifies this so that I just get 8.3 times 10 to the -3x, because I would multiply those two together. So if you solve for that, right, by dividing through and then you have x, you should find that x equals 1.9 times 10 to the -8th, okay? So if I take a look at this value, it would be, in order to check 5% rule, it would be X over the initial concentration, which was 8.3 times 10 to the negative third. Okay, if this is 10 to the negative eighth up here, I'll be within that 5% rule. This is much smaller than 10 to the negative third. So a very small numerator, a very large denominator in comparison means a very small number coming out. It'll be under 5%, even when I multiply by 100. So I'm good to go there. 5% rule applies. Okay, 1.9 times 10 to the minus 8. So this is what the chloride ions equal, okay? But what does the silver equal? Well, the silver was 8.3 times 10 to the negative third plus X, so it's going to be plus 1.9 times 10 to the negative eighth. Now, we just finished stating, okay, this is for silver, we just finished stating how this value, X, is so much smaller, less than 5%, of 8.3 times 10 to the negative third. So if I attempt to add it, right, I'm going to just get back approximately 8.3 with rounding to sig figs times 10 to the negative third. It's not going to play an effect. That's what we just said with the 5% rule, was I can ignore adding X here. So it would make sense if that's what X equals. When I add it here, I would ignore it again. It's just going to be this value. So this is the value of silver in the common ion, okay? And then the value of chlorine, the chloride ion, is going to be equal to 1.9 times 10 to the negative eighth, okay? Now, in a normal example, where we're not having common ion, this value would not be present in the ice chart. It would just be X and X. And so these two would equal one another. Ag and Cl would have the same concentration. That's not true here because, again, the nitrate is leading up to the silver, where it's releasing a bunch of silver before the silver chloride ever hits the solution. All right, so in a solution of silver chloride, the silver is going to be a mix of both the silver nitrate and the silver chloride, but the chloride itself is only going to come from the silver chloride. So the question was, going all the way back up, what is the solubility, calculate the solubility in grams per liter of silver chloride in the AgNO3? So the question becomes, which of these values do I use here? Well, I need it to be representative of just the silver chloride. So the answer is I use the chloride value when I get ready to solve this. And that's because this value right here, the silver, is not representative of the silver chloride alone. It represents the silver for the silver chloride and the silver nitrate. So it would not be appropriate to use this in calculating the solubility of the silver chloride in solution. Okay, but the chlorine, the chloride ion, comes directly from the silver chloride. So therefore, it is an accurate representation of the concentrations of the silver chloride. So what we can do then is we can say, all right, 1.9 times 10 to the negative eighth moles of silver chloride to every 1 liter. Okay. And if I want to find solubility in grams per liter, I would need the molar mass of silver chloride, which is approximately 143.4 grams of silver chloride to every 1 mole of silver chloride. So you put all of that together and you come out with 2.7 times 10 to the negative 6 grams per liter. This would be the correct answer to the question. All right, now just to give you a check, a reality check on that answer, I'm going to give you a value that wasn't provided in the initial equation. So normally, if I take silver chloride and I dump it into water, the solubility of silver chloride in water is approximately 1.9 times 10 to the minus third grams per liter. So does this answer make sense? what has happened to the solubility? Has it gone up or down?
Decreased.
It's decreased, exactly. Now, does that make sense?
Yes.
Yes. Hopefully it does if I walk through all of it, right? But yes, it makes sense for the following reason. If this is the solubility in pure water, where nothing's hindering it, now I'm saying what happens if instead of pure water, I have water that is polluted, for lack of a better term, with a bunch of silver ions to start with? Well, that's going to decrease the solubility because there's not as much room for silver ions in solution anymore. Again, going back up to the main equation, this is Le Chatelier's principle here. It's at work by saying if instead of just water being present, I have a bunch of the reactant, or I'm sorry, a bunch of the product present from a common ion, then it should decrease the solubility, meaning more of this should stay out of solution as a precipitate. Okay? So that is the common ion effect. Now, we're going to switch gears here, and we're going to look at redox reactions. So I'm going to walk you through a single redox reaction, and then we will talk about this some more on Thursday. So let me clear this briefly. All right. So switching gears, we're now going into the electrochemistry portion of lecture. So this is what we were technically supposed to start at the end of last week, but throughout most of this week, what we're going to be working on is electrochemistry. So for electrochemistry, I'm giving a fair warning here. You have to understand and be able to utilize oxidation numbers. So we talked about that briefly during the Chem 111 or Gen Chem 1 review. That is going to come back here, and you have to have a good grasp on how to assign oxidation numbers. So oxygens are normally 2-, hydrogens are normally 1+. Any type of metal is going to be whatever type of ionic state it's in, unless it's solid, in which case the oxidation state is 0. So going along that general premise, you're going to need to have a good grasp of that as we move forward. All right. So I want to create or put up an unbalanced redox reaction. So the one that we're going to take a look at today is going to use iron 2+, and we're going to add that to the chromate ion, which is Cr2O7, 2-, and that is going to yield iron 3+, and chromium 3+. Okay. So when we say redox, redox stands for reduction oxidation. So a redox reaction is going to be a reaction that primarily is focused on what? What are we going to try to balance in these reactions besides the elements themselves?
The charges.
Exactly. Okay. Redox is going to focus, we're going to talk about batteries later on, how to create batteries and galvanic cells and all of that sort of thing. But in order to understand that, what we have to first outline is how many electrons are being passed back and forth during this reaction, because the electrons are where we're actually going to generate the electrical current for any type of battery cell that we might examine later on. And that's how most of our batteries work, whether they be lithium ion, whether they're cadmium nickel, cadmium zinc, any of these types of batteries, a lead acid battery, you're going to be dealing with a transfer of electrons back and forth from metals, which can undergo redox reactions. All right. So this is currently unbalanced. You can see that by the chromium. I've got 2 on the left side and 1 on the right side. All right. The first thing you need to do is break these down into what's known as a half reaction. Okay, so there's 2 types of reactions. We have the oxidation and we have the reduction, and those can each be broken into what's called a half reaction. Now we will combine the half reactions at the end back into a whole reaction, and that will be once we balance the electron transfer that's going on each side. So for the oxidation, before we can really determine that, we need to know what oxidation is, okay, to determine the half reaction. So this is where you might do oil rig or Leo Gur or whatever your mnemonic of choice is, okay? Where loss of electrons is oxidation, gain of electrons is reduction, okay? Or for the oil rig, it would be oxidation is loss, and then reduction is gain. So it doesn't really matter whichever one helps you keep it straight. You need to be able to keep track of that. So what is being oxidized here? Iron or chromium? This is where you're going to have to understand your redox numbers. Okay, this one is fairly easy to tell which one's being oxidized. What is oxidation? A loss or a gain in electrons? A loss. Loss of electrons is oxidation. Okay, so in this case, iron is oxidized. Why? Because iron is going from 2+ to 3+. Okay. Now keep in mind, plus represents the proton charge or the electrons that have been removed. So iron has lost an electron in this process, correct? If it's gone from 2+ to 3+, I had to take away an electron in order to create that additional plus charge. So I can write the half reaction for the oxidation as iron 2+ is going to go to iron 3+. All right, so then that means by default, the other one has to be the reduction. And for the reduction, we've got chromate, 2-, goes over to Cr 3+. Okay, now in order to properly understand this, you're also going to need to understand the oxidation numbers. So what is the oxidation number for oxygen on a regular basis?
-2.
Correct. Right? So if I have 2- and it's going to be times 7, then what would be the charge there? 14-, right?
Mm-hmm.
So the chromium must be what? And this should have a 2 here, sorry. Okay, so the chromium has to be what to balance that out?
6.
6, that's exactly right. Okay, so if the chromium is 6+, there's 2 chromiums, so that means that it would have a total of 12+, which is correct because there's a total charge of 2- here. So 12 minus 14 is -2. That's our 2- charge. Okay, so again, oxidation numbers, you have to understand how they're going to work here in order to keep track of this. And if I'm going from 6 to 3, that's a gain in electrons because I've gone from a more positive state to a less positive state. I have to be gaining negative charges back in order to do that. I have to be gaining electrons. So this is the reduction half. Okay, so now what we need to do is anytime you have just the metals, you can balance them with electrons. So that's easy enough to do. But anytime you have oxygens or hydrogens, you have to start using water in order to balance them. Okay. So what we're going to do here is take a look at the oxidation first. This is easy because all it is a metal. So if I go from Fe2+ to Fe3+, I have to add plus electron here in order for the charges to balance out, right? Because the net charge over here is going to be 2+. And so if the net charge over here is 3+, I need to add a single minus in order to make it go back to 2+. So I add 1 electron in order to balance that. So that is my balanced half reaction for the oxidation. Now the reduction is going to be more complicated here. So for the reduction, I'm going to start by balancing the oxygen here using water. So I'll rewrite this and I'll say Cr2O7 2- is going to go to Cr3+ plus how many waters do I want to balance out the oxygen? H2O, so I get a single oxygen per water. So how many of them will I need?
7.
7, good. Okay, so 7 H2O. Now there's the chromium. There's a 2 in front of the chromium here since I've already balanced the oxygens. So I need a 2 in front of the chromium here. Now, the introduction of water has introduced hydrogen, which was not present on the left-hand side. So now we're going to add H+. So this is a technique that's called redox in acidic media. Okay, you can also do a redox in basic media, which we will take a look at on Thursday. We're not going to do that right now, but that's where you would use hydroxide instead of H+. All right, so for it to be in acidic media, I can just simply grab H pluses and say, how many H pluses would I like here? What do you think,
14.
everybody? 14,
14.
exactly, right? In order to make it balance. So that's the nice thing about H plus is it comes by itself. So I can just put whatever number I need in front of it and that will balance out. So now I have finally the balanced half reaction for the reduction side, a bit more work there, okay? But there is still one thing I need to consider. What have I not added here? That was the whole goal. We're trying to balance what besides just the ions? The electrons, right? So I need to keep track of the charge to see where the electrons should be. So if I take a look, the total charge on this side of the equation is going to be, well, I have 14 pluses from the hydrogen, and then I've got one that's a 2 minus. So 14 plus and 2 minus is going to come out to a net of plus 12. And then over here, I've got 2 chromiums at 3 plus a, excuse me, getting tongue-tied. I have 2 chromiums at 3 plus a piece, and water is neutral. So over here, I have a total of 6 plus. Now, where do I need to add electrons to make this balance out?
The reactants.
Exactly. If I have 12 plus, electrons are negative. So I need 6 of them. I have to add 6 electrons over here in order to make this a 6 plus. And then electronically speaking, I'm balanced over here. All right. So what we do is we say, all right, let me clear this down here left over from the common ion. Okay, so now we're going to set it up so that we've got everything and we're going to combine the whole reaction back together. So what I'm going to do to start is take the oxidation, which we said would be iron 2 plus, okay, is going to go to iron 3 plus an electron. Right? Now, I'm going to line this up so it's easy to put everything together while we're viewing it. Okay, so I'm going to have to back up a little bit as I'm starting to add things here. So I said over here, I'm going to have 14 H plus one of the chromium, chromate, I should say, bundles, plus 6 electrons, right? And then over here, I said that I would have 2 chromium ions at 3 plus apiece, plus 7 H2O. So the last thing I have to do is balance the net electrons. I did it for the reactions on each half reaction. So I need to multiply this oxidation by 6 because I need 6 electrons over here to pass 6 electrons down here. And notice the 6 electrons here are on the reactant side. When I distribute this 6 over here, they're going to be on the product side. So they will cancel one another out, just like a spectator ion or something of that nature. So I distribute 6s here. That means I also distribute 6 iron 2 plus and 6 iron 3 plus. And then I get the final reaction. Okay. So what would the final reaction look like? It would be 6 iron 2 plus. Now that's it for the reactant side on the oxidation, plus 14 hydrogen ions, plus the chromate ion. That's it for everything on the reactant side, combining both equations. the electrons have dropped out, will yield 6 iron 3 plus 2 chromium 3 plus 7 H2O. And here is the balanced redox equation for what we had. Now this was balanced in acidic medium, all right? So like I said, I'm not going to go through an example for basic yet because it would run up too close to the quiz time and I want to give people a few minutes here. But when you do your basic, what you're going to do is come up to the step where you add H plus, and then when you get to the step where you add H plus to your redox, you'll add an equal number of OH minus in order to create water. And then you'll see how many waters you cancel over on the right, and the remaining will be hydroxide content that you'll be liberating. So again, don't worry about that right now. We'll take a closer look at that on Thursday after the exam is over. Right? So what I'm going to do now, I'm going to stop sharing, and I'm also going to stop the recording because this is where I want to cut it off and put the lecture content up on YouTube. So let's go ahead